We are all scutoid. A brand new shape explained. The New Yorker has an article. A Play-Doh figure of two scutoids. Researchers first observed the previously unnamed shape in a computer model. They then went to nature and found it in abundance. Until last week, the world of science was unaware of the scutoid. The scutoid is a basic three-dimensional shape like a cube or a sphere, but not like either of those things. It's more like a column with half of one end lopped off at an angle. Is that what I'm seeing here? Half of one end. Like, is this the part that's lopped off? It's a prism with a zipper. Javier Buceta, a biophysicist at Lehigh University and one of the scutoid's discoverers, told me excitedly. This was not so helpful. What matters is that mathematicians had never before conceived of the scutoid, much less given it a name. What matters even more is that scutoids turn out to be everywhere, especially in living things. The shape, however odd, is a building block of multicellular organisms. Complex life might never have emerged on Earth without it. The hyperbole is quite thick. Its existence allows you to understand the fundamentals of morphogenesis and development, how cells act together when they're forming and developing. That's interesting. One of the many mysteries of living cells is how they manage to blossom into coherent many-celled units. A person or a platypus begins with a single cell, which divides into more cells, which also divide and subdivide. Some of these, the epithelial cells, are destined to become tissues and organs. The cells collect into layers, which bend and fold into greater than sums, ovaries, kidneys, a heart, etc. In part, it's a packing challenge, a geometry problem. As the layers twist and curve, the individual cells change in shape in accordance with the whole, and they do so as efficiently as possible. Buceta offered the analogy of a Roman arch. You can form rectangular cobblestones into a straight row, but to form a curve, the stones must be reshaped so that one face, the bottom end, and on the inside of the arch is smaller than the top face. The stone is no longer rectangular. It's more like a pyramid with the pointy end lopped off. Mathematicians call that shape a frustum. Yes, they do. Similar dynamics apply in biology. When epithelial cells packed together in a layer of flat tissue, each will often take the shape of a column with 5 or 6 sides, like a prism. That makes sense. As the tissue grows and bends, some cells deform, with one end becoming wider than the other. This allows the tissue to have a larger area on its outer surface than it does on its inner side. Right. Biologists had long assumed that these cells acquire the shape of a frusta, as in a Roman arch. A frustum may be 4-sided like a pyramid, but can also have more sides than that, sure. But as Buceta and his colleagues reported in Nature Communications, this isn't always the case. The way those cells pack together in 3 dimensions is actually kind of weird, Buceta said. The researchers developed a computer model to simulate what happens to individual cells in curved tissue. The cells pack together along faces and edges, but building and maintaining those borders takes energy, and each cell wants to use as little as that of energy as possible. The larger the contact, the more energy they have to expend, Buceta said. The team found that the total length of these contacting borders is smallest and the packing most efficient when at least some of the cells take the shape of scutoids. Where you have curvature, you have scutoids. Okay, this is pretty interesting. Buceta was keen to send me a diagram of a scutoid to explain what one looks like, but I pressed him for a verbal description. Picture an upright column with 5 sides, 2 pentagons, one at the top, one at the base, attached point to point by 5 lines. Yeah, I can do that. That's easy. I can draw that. pentagonal prism. Let's draw. Let's draw a picture. So here's a pentagonal prism. Well, no, that's not a good looking foreshortened pentagon. A pentagonal prism. Can't see that side. You can see this one though. And then bingo, bongo, bingo, bongo. Okay, so there's the pentagonal prism. And suppose the pentagonal column is a tent, and that one of the vertical edges where two of the 5 faces meet. So one of these edges is a zipper. Okay, so this we're going to now imagine is a zipper. Okay, browser on top, I hear you. So I'm drawing a picture of what they're describing here. And now how can I just have to get rid of the browser. Or no, I can move the browser. No. Move the browser. And now, oh God. There's my scutoid so far. And I'm following the description in here where I've got suppose this pentagonal column is a tent, and that one of the vertical edges, this one here kind of highlighted in green here, is a zipper. Now unzip it from the bottom to midway up and fold back the flaps. So I zip up to here. I mean, are they just saying that I'm truncating this vertex? Like, am I just taking out this little chunk? Right here? It does not seem that hard to visualize. So this blue part here is just cut out. So we're just taking a knife and just slicing through one of the corners. Why is this hard to visualize? The internet quickly jumped in to help. A few minutes later, after we spoke, Busetta sent me a link to a YouTube video in which a young boy displayed a Lego-like model of a scutoid. Over the weekend, someone updated Wikipedia with an entry for the shape, describing it in part as a geometric solid between two parallel surfaces in which the boundary of each of the surfaces and all of the parallel surfaces between them is a polygon, and the vertices of the two end polygons are joined together by a curve or a Y-shaped connection. Sure. At first, the researchers didn't know what to call it. When we found the shape, we said, let's talk to the mathematicians. For sure they know the name of this. But they couldn't give us a name because it didn't have a name. We had to find one. They noticed that the shape vaguely resembled the back end of a beetle, a structure called a scutellum, hence scutoid. The team's accomplishment was more than theoretical. Okay, so the question I have right now is how packing these things together, how does that generate curvature? Like, say, I would imagine that this part up here sort of is, would be part of the sort of outer part. And then this part down here, I would imagine, is the inner part of an organ, right? When you have these cells packing together to form the wall of an organ. And I could believe that, for example, if you didn't have this wedge cut out, that the curvature couldn't happen, right? In other words, it would just be sort of like a flat layer with no curvature to enclose an organ. I could believe that. But it's not totally clear to me how this generates curvature. I would like to see that. It's not that I don't believe it. Having predicted the existence of the scutoid, the researchers went looking for it in nature and soon found it in abundance. They examined the developing embryos of fruit flies and watched as individual epithelial cells divided, aggregated, curved, and folded to form salivary glands and egg chambers. Visible within the tissue matrices were scutoids, more where the tissue curved most, none where the tissue was flat. And scutoids are as likely to be found among mature cells as in developing tissue. So I asked, even at this very moment, are we made of scutoids? Yes, he said. Yes, we are. Since they're scutoids, does that mean there are scutes? Almost certainly. And the scutoids are like, are they little babies? Is that what you do with the oids? Postfix, whatever you call those, suffix. Is that what those are called? I don't know any words. Like a scutoid is a scoot, but a little different, similar to a spheroid. Like, what does the IOD do to a noun? I think there are illustrations of the packing on nature. Okay, I'll look it up. For now, Buscetta is satisfied with the name. In our line of work, you don't normally have many opportunities to name something. Honestly, in the beginning, we couldn't believe that nobody before us had named this shape. I mean, geometry has been around forever, the square and the circle. It's really wonderful that we could name something so fundamental. Okay, cool. I'm happy for you, for sure. Scutoid packing.